Hi, I'm Maria, and with Peter and Daniel, we'll be talking a little bit about weight q-multiplicities for representations of the Lie algebra SP6C. Here's an outline. First, we'll talk a little bit about Kostant's partition function, and then we'll talk a little bit about computing the alternation sets for Kostant's weight multiplicity formula. So let's start with an example of a vector partition function, since Kostant's partition function is a vector partition function. So let's say we're at Chuck E. Cheese. We play games, we get tickets, and we exchange tickets for prices. And let's say that at this Chuck E. Cheese, we have three types of tickets here. They are run a circle, so we might call them coins. So we have the red coin, the blue coin, and the green coin. And the red coin and the blue coin cannot be exchanged for each other in any way, shape, or form. And one green coin is equal to one red coin plus one blue coin. So let's say there's this unicorn plushie we really want, and it costs 5 red coins plus 4 blue coins. The question we can ask is, how many ways can we pay for this unicorn plushie if we want to use the red coins, blue coins, and green coins? If we think of the coins as vectors instead of coins, then this is a vector partition function. And one way of paying for this plushie, we call that one partition. Vector partition functions are really cool. They have applications to all these areas of math. We specifically care about the applications to representation theory because that's what Kostant's partition function is used for. So now let's shift our perspective. So let's talk about the roots of a Lie algebra of type C3. So everything here is a vector. So these simple roots, these alphas, are just linear combinations of the basis, the standard basis elements, like the ones we use in calculus. And these positive roots, these betas, are just linear combinations of the simple roots, the alphas. And then we have a weight, which just means vector, and it will be written in as a linear combination of the simple roots, of the alphas. So then now we can define Kostant's partition function. So Kostant's partition function takes in a weight mu, a vector mu, and it tells us how many ways we can write mu as a linear combination of the positive roots, betas. And it's specifically a non-negative integral linear combination. What that means is that the coefficients of the linear combination have to be non-negative integers. So thinking about the unicorn plushie example, the weight mu would be the price of the plushie, and the positive roots, the betas, would be the coins that we would use to pay for the plushie. Then it makes sense that it's a non-negative integral linear combination because we can't pay negative coins and we can't pay fractional coins. So there's also what's called the q analog of Kostant's partition function, which is quite similar, and it takes in some weight, some vector mu, and it spits out this polynomial in q, and q is really just a variable. We don't really care what q is. What we care about is c sub I, which is the number of ways we can write mu by adding up exactly I positive roots, right? So thinking back to the unicorn plushie, c sub I would be the number of ways we can pay for the plushie if we want to use exactly I coins to pay for it. Now, since the q analog is still keeping track of every single partition, of every single way of paying for the plushie, if we set q equal to 1, we recover the normal Kostant's partition function. The thing about Kostant's partition function and its q analog is that there aren't really close formulas in general for it. There have been some successes in finding close formulas for low-ranking classical Lie algebras and for some very specific inputs, but there aren't really close formulas in general. So to add to the literature, we found a closed formula for the q analog of Kostant's partition function for a Lie algebra of type C3, and it turned out to be this really large sum. We won't really talk about it, but that is what it ended up looking like. So now we can move on to Kostant's weight multiplicity formula, which looks at a weight mu in a highest weight irreducible representation L of lambda, and it tells us the multiplicity of the weight. And you might wonder what the relationship is between the multiplicity formula and the partition function, aside from having Kostant in the name. And if you look at the sum, you might notice that it is mainly made up of Kostant's partition function. And that is why we care about Kostant's partition function, because it factors into this weight multiplicity formula. There's also a q analog to the multiplicity formula, and the only difference is that it uses a q analog of Kostant's partition function. And like with the partition function, setting q equal to 1 recovers the normal multiplicity formula. But since what we care about is the same for the multiplicity formula and the q multiplicity formula, we're just gonna focus on the normal multiplicity formula. So now let's break down what each part of this formula means. So we have the fancy p, Kostant's partition function. We have mu, which is a weight, just some vector. We have lambda, which is also another vector, a very special vector. We call it the highest weight, but it's really just some vector. We have rho, which is defined to be half the sum of the positive roots. Then we have W, the Vowel Group. We'll talk about that later. We have sigma, an element of the Vowel group. And then we have L of sigma, which is the length of sigma when it's in its minimal form. And about the minimal form part, you can think of that like a permutation. Like when you write a permutation in cycle form, you can always write it longer. So we only care about the length in the minimal form. So now we can define the Vowel group. Geometrically speaking, it is a finite group of orthogonal transformations generated by simple root reflections. Computationally speaking, it is a group generated by these SIs via function composition. And these generators act linearly on the simple roots alpha 1, alpha 2, and alpha 3. So then that brings us to some complications when we are trying to compute the multiplicity formula. The first one is something we talked about before, which is the lack of closed formulas for Kostant's partition function and its Q analog. The other one is that the size of the Vowel group grows exponentially factorially with the rank of the Lie algebra. So I'll show you what that means. So for Lie algebra of type C2, the Vowel group has 8 elements. For C3, 48 elements. For C4, 384 elements. In general, is 2 to the n times n factorial elements. So you can see where that exponentially factorially comes from. And also in general, the Vowel group is isomorphic to the group of sign permutations in n letters. So we are working with the Lie algebra of type C3, so we only have 48 elements to worry about. So it's not as bad as it could be, but it's still a lot, especially when we remember that we are summing over the elements of the Vowel group. So our multiplicity formula is a sum of 48 terms. Now I'm going to pass it off to Peter, who is going to talk a little bit about what we can do about the Vowel group being so large.
Thanks, Maria. So as we talked about already, we want to simplify Kostant's weight multiplicity formula as much as possible. So what can we do to do that? Well, if we remember, Kostant's partition function counts the number of ways that we can write a weight as a non-negative integral linear combination of positive roots. So if this is our weight and it has coefficients a, b, and c, and either a or b or c is less than 0, then immediately we know that Kostant's partition function is going to return 0 for that particular weight. That actually turns out to be really useful information, and we're going to combine that information with the fact that Kostant's partition function evaluates to 0 if and only if its Q analog also evaluates to 0. So what we're going to do is define a Weyl alternation set, and that's basically just the element sigma of the Weyl group, which when you consider their corresponding term in Kostant's weight multiplicity formula, if that term is greater than 0, so if it's non-trivial, then that element is going to be in our alternation set. Otherwise, it's not going to be. So basically, it's just all the sigma that give us a non-zero term. And we say that if a term of the weight multiplicity formula equals 0, it contributes trivially to our sum. Otherwise, it contributes non-trivially. And so that's some language that we're going to be using later on. And that actually allows us to simplify our computation a little bit. So if we know what the Weyl alternation set is, then we could simply sum over all the sigma in that alternation set. And we would actually get the exact same thing as if we summed over the entire Weyl group, because all of their terms would just give us 0. So what we want to do is we want to classify the alternation sets. That is how we would be able to simplify our weight multiplicity formula. But there are, as of right now, a lot of possible alternation sets. Since the Weyl group has 48 elements, there are 2 to the 48 potential alternation sets. And so what we want to do is cut that down as much as possible. And it turns out we can do a pretty good job. So to start, we'll recall that this is our weight multiplicity formula. And this part right here is what we're plugging into Kostant's partition function. But what this thing is just a vector. And so it has coefficients that we can write as C1 sigma, C2 sigma, and C3 sigma. And these coefficients are going to vary only based on sigma because we have fixed lambda and mu, and rho is also a fixed vector. So we can look at Kostant's partition function evaluated at these three, with these 3 coefficients at this vector, and we can check, okay, if all of the coefficients are non-negative integers, then that sigma is in our Weyl alternation set. And so what we've done is, this is just for illustrative purposes. You don't have to actually see what these cells represent, but these for each sigma in the entire Weyl group, this is exactly what the coefficients turn out to be, as represented as a linear combination of the components of lambda and mu. And it turns out that all of these highlighted in orange are guaranteed to be negative. And that's actually really useful information, because if that because we know that since that coefficient is negative, that particular sigma could not possibly be in a Weyl alternation set. And so that actually allows us to cut down how many elements could be in our alternation sets down to only 17 of the sigmas in the Weyl group. And that's really great because that reduces us all the way down to only 2 to the 17 potential sets, which could be alternation sets. But it turns out we can do even better than that. So here is a smaller table showing all of the remaining coefficients that we're going to be working with for the rest of the talk. And we're going to start by performing a small change of variables. So you'll notice that all of these values highlighted in purple are the exact same. So we're going to let lowercase a equal that value, let lowercase b equal this expression, etc. And it turns out that these variables a through r, all lowercase, are going to represent these expressions. And what we're going to do is we're going to say, okay, if we put a subscript 0 in front of that lowercase letter, then it means that expression evaluates to something greater than or equal to 0. And if we put a subscript 1, then that expression evaluates to something less than 0. We're also going to say, we're going to use capital letters to denote the terms of Kostant's weight multiplicity formula, or the potential terms. So note that this thing can be written exactly as Kostant's partition function evaluated at this vector with just coefficients in that using that change of variables that we have just defined. And these are all exactly the same thing. It's just kind of a easier way to visualize what we're doing. So now we're going to talk about how we convert between these capital letters, which are equivalent to things that look like this, and logical statements, which is what we're going to use to reduce down potential alternation sets. So let's say that you have this first letter A, and that basically is equivalent to this. And we're going to suppose that it contributes non-trivially to the weight multiplicity formula. Recall what that means is that this term evaluates something that is greater than 0. Well, what that means is that this coefficient and this coefficient and this coefficient must be non-negative integers. And so we write A0, D0, and J0. Let's say it contributes trivially now. Well, then it has to be that one of these coefficients is, at least one of these coefficients, is negative. So we write that if A contributes trivially to the weight multiplicity formula, then A1 or D1 or J1 is true. And so we basically use that kind of thinking to reduce down what our Weyl alternation sets could be. And
thanks, Peter. Right, so with these logical statements now defined, we can construct these other two types of contradictions, which will sufficiently help us achieve our main results. The first of which is a type 2 contradiction, which we defined to be having some ci sigma, those coefficients from earlier, where it needs to be both negative and non-negative simultaneously. We also have type 3 contradictions, where we have which imply that some subset of m, n, k, and x, y, and z, which are the weight coefficients, is totally negative. So an example of this would be if you're given logical statements A1, D1, and J1, and their negations A0, D0, and J0, then A1 or D1 or J1 and A0 and D0 and J0 is an example of a type 2 contradiction. So in this statement, you also might look at these subcontradictions A1 and A0, D1 and D0, and J1 and J0, where they're all saying something of this form. This coefficient is greater than or equal to 0 and less than 0, which is a contradiction. All these statements, right, we're looking at these triples, and we're motivated to look at these triples because of the way we defined logical statements previously. We had that A contributes trivially if and only if A1 or D1 or J1 is true. And we can play a similar game with the right-hand side, where we have that D contributes non-trivially if and only if A1 is 0 and D0 and L0 is true. But in this case, we can just grab the A0 and D0, and the L0 is kind of irrelevant here, so we leave it on the side. We can then grab the J0 from stating that E contributes non-trivially from the right-hand side as well. And so we're left with this set of logical statements about the contributions of these coefficients or expressions to the constant weight multiplicity formula. We can take this one step further to identify the supporting groups or supporting sets by noting that A contributes trivially if and only if 1 is not inside of that set S, and that D and E contribute non-trivially if and only if S3 and S1, S2 are inside of S. So therefore, since that set, since we have an equivalent, this being equivalent to a contradictory statement, we now have that S can never be an alternation set, because if we had S be an alternation set, then in some way, some shape, or some form, we would arrive at some contradiction to the constant wave multiplicity formula conditions, which are the non-negativity and non-integrality conditions. And so going back up the tower, we recall that the main base of this tower are these little two tuples of A1, A0, D1, D0, and J1, J0. And in fact, this motivates the way we want to construct these type 3 contradictions and how we'll proceed with them in a similar fashion. So consider A1 and B0 with the weight coefficients being in the natural numbers. Then A1 is equivalent to this inequality here, and B0 is equivalent to the inequality here. And so if we take some nice combination of them, sum of them this way, we have that -1 or negative m minus 1 is greater than or equal to 0. But this is a contradiction because we assumed that m was a natural number. And we have found a whole host of contradictions like this type, where there's these two tuples or three tuples, which force m, n, k, x, y, z, or some subset of them to be strictly negative. I would also like to remark that this is not an exhaustive list of type 3 contradictions. We actually also found some type 3 contradictions which did not contribute additional information besides these ones, so we decided not to include those. But nonetheless, here is a list of these contradictions which we use to reduce those 2 to the 17th sets, also with the type 2 contradictions, all the way down to 150 possibility supporting sets, which we called Weyl alternation sets. And so I'll pass it off to Maria now, who can talk about how we can combine those contradictions to proceed with our final refinement.
So we find that contradictions type 2 and type 3 don't always happen in isolation. So for example, take when the multiplicity formula is equal to -d. So d contributes non-trivially and everything else contributes trivially. So then, like we said before, this would imply this logical statement here. And if we come through it carefully for contradictions of type 2, we won't find a full contradiction. And if we come through it for contradictions of type 3, we also won't find a full contradiction. So there are no contradictions of type 2 or type 3, but let's look for both of them together at the same time. So here in this logical statement now are highlighted two parts of it. And you notice that in these two parts, you have A1 and A0, which is a contradiction of type 2, D1 and D0, also a contradiction of type 2. And then we have J1 and L0, which is a contradiction of type 3. So since these are also contradictions put together, these two being together in the same logical statement is the contradiction, which means the whole logical statement is the contradiction. And so the multiplicity formula can never equal -d, and its corresponding alternation set can never be an alternation set. Using this process, we get down to 46 possible alternation sets. So now all that's left to do is to prove that these 46 sets actually appear as alternation sets. The way we do that is by construction. So by finding lambdas and mu's that induce these sets as alternation sets. So we do that, and so here in this table are the 46 sets together with a lambda and a mu that induce them as alternation sets. So that brings us to our main result, which is that the 46 sets I showed you are the only alternation sets when lambda and mu are dominant integral weights. So when the coefficients of lambda and mu are non-negative integers. And now I'm going to pass it off to Daniel, who's going to give us an example of how we can apply this result.
Thanks, Maria. For an application or result, let's consider mu equal to 0 and the highest root of SP6, lambda equal to 2 omega 1 after a change of basis. Then if we evaluate the expressions a through r, we find that a, d, e, j, and l are the only non-negative coefficients. And so by case 41 of our main result, we have that the q-multiplicity formula must be aq minus cq minus dq. Then evaluating these aq, cq, and dq's using the summation formula that Maria had described us earlier, we find that the q-multiplicity must be q plus q cubed plus q to the 5th. And this matches the famous result by Lustig. Furthermore, if we evaluate q at 1, this yields 3, which is as expected. Fantastic. So why is this so? Why do we care? Well, computations become incredibly easy. There are only 46 possibilities for supporting sets, as opposed to 2 to the 48th possibilities for supporting sets. For some future directions, we can consider a geometric angle trying to describe the Weyl alternation sets via patterns on the root lattice. We can also consider an algebraic angle where we try to find an algebraic relation between lambda and mu, where they're both in dominant chamber. We can also explore poster relations of Weyl alternation sets, and we can also do similar work for other Lie algebras. To conclude, we'd like to acknowledge the support and mentorship of Dr. Pamela Harris this summer. It's been a blast working with her. We'd also like to acknowledge and thank Williams College for funding our research and our work. And we'd also like to thank the YMC organizers for hosting this conference. And we'd like to thank you, the audience, for listening to our talk. To conclude, Here's our contact information and some references if you're interested in searching something further.